Okay, troops. We're finally there. We've got to interference by division of amplitude. If you see an oil spill on the ground, it's a random spectrum you see. If you see a soap bubble or a back of a CD, it's got a spectrum on it. That's an interference pattern that's produced by interference by division of amplitude. And there's a way, there's an experiment we can do to get a regular interference pattern where we can measure not only the fringe separation on the interference pattern, but we can measure the wavelength of the light that is producing that interference pattern. So, this is sometimes called the Air Wedge experiment or demo. Right, we are doing a derivation of the relationship for interference by division of amplitude, the Air Wedge. Not division of wavefront, that's the double slit experiment. This is division of amplitude. And by an air wedge, what we mean is if we take two microscope slides. Now, hopefully you know what a microscope slide is. Microscope slides are a little glass rectangular slide you put somewhere, look under a microscope. And we put something very thin at one end of those two microscopes, and it makes a little wedge of air. There's air in there. Now that very thin object might be a sheet of paper or something. Now, thin, the thickness of a sheet of paper, on a human hair or a wee bit of wire or something like that. Something very, very, very thin. So that would be the thickness of our sheet of paper. That distance there is D. Thickness of a sheet of paper. And when light comes down and shines into it, then some of the light gets reflected from the top surface of the top glass slide. Now we're going to ignore that. What we're interested in is we're interested in light travels into that top glass and it reflects off the bottom surface of the top glass. But some of the light continues down into the air wedge, through the air wedge, and it reflects off the top surface of the bottom glass. And that reflected ray comes back up and exits out. And these two, that reflected ray and that reflected ray interfere with each other. Why is it called division of amplitude? Because some of the energy of the wave is reflected here, and some of the energy or the amplitude of the wave is reflected from here. And those two waves interfere, and there's a path difference between the two of them equal to that distance down and back up again. Ray number 2 has got an extra path of down and up, so it's the thickness of the air wedge, twice the thickness of the air wedge at that point, 2t. 2t is equal to the path difference. Remember, the refractive index of air is 1, so we don't need to worry about the refractive index this time. The path difference between ray 1 and ray 2 will be twice the thickness of the air wedge at that point. And if that's equal to a whole wavelength, we will get constructive interference. If it's equal to half a wavelength, we'll get destructive interference. Now here's the key, here's the hook. If you put your eye there, and you move your eye either that way or that way, not just your eye, head, if you move your head that way or that way, what you will see is you will see regions of constructive and destructive interference. You'll see a pattern like this. You'll see a dark line, light line, dark line. That will go light, dark, 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 light, dark. And the distance between those fringes is the fringe separation delta x. Now that happens when you move your eye a certain delta x. It's because that path difference has increased by a wavelength. So down and back up is equal to a wavelength. So that extra length there is half a wavelength. Because it goes down and back up again for a whole wavelength to get your next fringe in your interference pattern. Now, we've got two similar triangles here. We've got this D, which is the thickness of the paper. L is the length of the glass slide. And we've got this wee triangle here, delta x and lambda over 2. And because they're similar triangles, we can do this. We can do L over D, that horizontal side over that vertical side, will be in the same ratio as delta x over lambda over 2. And if we rearrange this to get delta x on its own, then just take that up to the other side, so that becomes L over D lambda over 2 equals delta x. And then switch it around, so delta x equals lambda L over 2D. Now that relationship is on your relationship sheet. Delta x is the fringe spacing. D is the thickness of the paper, or the object. It might be a hair, it might be a wire, something very, very small. That's in meters. That's in meters. That's the length of your glass slide. Meters. And that's the wavelength of the light. It's in meters as well. Everything's in meters, 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 meters. So by measuring delta x and measuring L and measuring D, we could work out the wavelength of the light. Or if we use a sodium light and we know the wavelength of the light, then if we know lambda, we know L, we know delta x, we can work out D, the thickness of a sheet of paper. We're going to try that. Yeah? Delta x is pretty tricky to measure. We need to use what's called a travelling microscope to measure the distance between the fringes. But, hey ho, that's it. Let's give it a go. Hello everybody. Right, today we're going to investigate interference by division of amplitude. Not division of wavefront, that's a double slit experiment. This is division of amplitude. And we're going to take two microscope slides and a little bit of printer paper. Now my printer paper, I am assured, is 80 GSM, grams per square metre. Right? And we're going to try and measure the thickness of a sheet of that printer paper. So I've cut a wee bit. And the way we're going to do this is, we're going to take the printer paper and we're going to put it at the edge of one of those microscope slides and then put the other microscope slide on top of it so that we have a little air wedge between the two microscope slides. Now, from our theory about interference by division of amplitude, then that air wedge, when light shines down on top of this, that air wedge will allow us to see an interference pattern that's produced from the constructive and destructive interference of the light that's reflecting from the bottom of the top slide and the top of the bottom slide. Now, we can't see that at the moment. We're going to use monochromatic light. We're going to use light from our sodium lamp. And we're going to shine that sodium lamp down onto the top of this. And we're also going to look down onto the top with a travelling microscope and see if we can observe an interference pattern. Now, if they're both shining from the top, they'll get in the road of each other. So we use this little chap here to help us, this little beam splitter. And what we're going to do is we're going to take our air wedge apparatus and we're going to pop it through this beam splitter. So there's my microscope slides slotted into the beam splitter there. A little air wedge between the two microscope slides, and that air wedge has been produced by that little sheet of printer paper. And I've put the printer paper in so that is about 4 millimeters from the edge of the microscope slides. And that means the length of the microscope slides, now length of a standard microscope slide is 76 millimeters. So I'm going to push 4mm of the paper in, so that we've got a length of microscope slide of 72mm. And then we're going to shine our monochromatic light in at one side, and we're going to look down on it from above and hopefully see an interference pattern. Now we'll need a travelling microscope to do this. So there's my travelling microscope. Let's pop this in and see what we see. So here's the wee experiment we're going to do. We have got our microscope slides set up with a sheet of printer paper stuck in at one end. That's producing our air wedge between the two glass slides. And we're going to use a sodium lamp. That's there. The sodium lamp's got a wavelength of 589 nanometers. We got that from a data sheet. The length of the slides, the microscope slides, are 76mm, but we're sticking the paper in 4mm, so the length of the air wedge is going to be 72mm. And then if we measure delta x, that's the fringe spacing, then we should be able to work out what small d is. That's the thickness of the paper. So we're going to rearrange this equation for d, and then we know lambda, we know L, we're going to measure delta x, and we should be good to go. Right, there's the air wedge set up, travelling microscope, monochromatic light source. Let's have a little look through here, see what we see. Now we just have to try and measure that with my crosshair, using the vernier scale that's on the travelling microscope. So my vernier scale is here. We're going to make a measurement when we are aligned with one particular fringe in the interference pattern, and then count 10 fringe spacings and make another measurement. See what we get. Now my vernier scale has been polished to within an inch of its life, but my initial reading is 4.70 centimeters. So I'm going to mark that down as my initial position, and then I'm going to count 10 fringe spaces. I'm going to move the travelling microscope and we're going to take another reading. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 fringe spaces. Right, there's my second reading. That's 4.92 centimeters. And I'll add that onto my diagram as well. Now that's 10 fringe spacings. So if that's 10, delta x is 0.92, so that's 2.2 millimeters. So therefore delta x must be equal to 0.22 times 10 to the minus 3 meters. And we can put that onto our list of data. So 0.22 times 10 to the minus 3, and then we're ready to pop them into the relationship that's on your relationship sheet. Okay, that's the relationship. It's on your relationship sheet for the air wedge. So we're rearranging it to try and get D, and D equals a lambda. That was our 589. Let's put all these values in. So 589 times 10 to the minus 9, 589 nanometers. Remember the length we used. The paper was sticking in about 4mm. It's a 76mm slide, so 72mm long. 72 times 10 to the minus 3. 72 times 10 to the minus 3. And that's all divided by 2 times our delta x, which was 0.22 millimeters. 0.22 times 10 to the minus 3. And if you do that on a calculator, we get 9.6 times 10 to the minus 5 meters. That's That's about 96 times 10 to minus 6 meters. Now, 10 to minus 6 meters is a micron, millionth of a meter. So that is 96 microns. Now, if we go and Google that, what's the thickness of 80 grams per square meter printer paper? Let's see what we get. But that's my paper. 80 GSM, grams per square meter. My apologies, I'm filming a computer monitor here, but there you go, 80 GSM, 100 microns, standard copier paper. What did we get? We got 96 microns. That's pretty close. So I'm pretty sure if we had worked out all our uncertainties as well, then we could be pretty confident with our result of 96 microns. There you go. That's division of interference by division of amplitude using an air wedge, measuring the thickness of a sheet of paper. There you go then. Right, here's the PowerPoint slides that go along with this part of the work. Division of amplitude experiment. An interference pattern can be produced using a setup called the air wedge. And we can use that to measure the thickness of very thin materials. There you can see the interference pattern that you would see when viewed from above. And in this case, that's a thin wire or a human hair that's been placed between the slides to make the air wedge. So there's this kind of side view of it, same as we had with our sheet of paper, our printer paper, between the two glass plates. And there's a photograph as well of an interference pattern that's been taken through a travelling microscope. It's a regular pattern of light and dark fringes. As the thickness of the air wedge increases, the path difference between the two rays increases, and at various positions along the length of the slide, the two rays will recombine constructively in phase or destructively when they're out of phase. And that travelling microscope can be used to measure the distance between those adjacent fringes. So remember, it's light that reflects from the bottom surface of the top slide and the top surface of the bottom slide. These two reflected rays have got a path difference between them. That path difference is equal to twice the thickness of the air wedge at a particular point, 2t. Remember, it's actually 2nt, where n's the refractive index, but the refractive index for air is 1. So the path difference is 2t. And if that path difference is equal to a whole number of wavelengths, then we get destructive interference. And that's because there is a single phase change when the light hits the top surface of the bottom slide. There's no phase change when the light hits the bottom surface of the top slide, because it's going from a more optically dense to a less optically dense medium. There's a single phase change. That's why when there is a path difference of a whole number of wavelengths, you get destructive interference. And the next dark fringe will be seen at a position delta x horizontally along the way when that path difference increases by a whole wavelength. There's the derivation of the relationship again. It's the geometry of similar triangles, but bear in mind that derivation is not examinable, but the relationship is on your relationship sheet and you should be able to use it to carry out calculations. Here's a wee worked example. A student places a thin copper wire between two microscope slides, and that creates an air wedge as shown in the diagram. Sodium lamp of 589 nanometer wavelength is incident on the apparatus from above. When viewed from above, a series of light and dark fringes are seen. There's a little image of that at the top. And the student uses a travelling microscope to measure 10 fringe spacings. That's recorded as 4.4 millimeters. And we've to calculate the diameter of the wire. Well, that is the d, small d, that's in the relationship. So you would rearrange your relationship and get d equals lambda L over 2 delta x. Your 10 delta x is 4.4 millimeters. So 1 delta x will be 0.44 millimeters. And if you put the length of the glass slide, 12 centimeters, and the wavelength
of the sodium light, 589 nanometers, into that relationship, you'll get an answer for small d of 0.08 millimeters. Part B, state why we chose 10 fringe spacings rather than just one. Well, that's because it's easier to measure 10. There will be less of a percentage uncertainty in our measurement of 10 fringe spacings rather than if we just tried to measure one of them. Part C, what effect, if any, would there be on the fringe spacing if a thicker wire replaced the original wire? And justify your answer. Well, if it was a thicker wire, then small d would be bigger, and in our relationship, small d, it's on the bottom of the right hand side of the relationship, so if small d is bigger, then delta x will be smaller, so the fringes will be closer together, and that of course is assuming that the wavelength of the light and the length of the microscope slides stays the same. That was a bit of a marathon. That's one of the trickier parts of the course conceptually. It's always worthwhile having another look at it, but there you go then.
Well, the troops asked to go over this in a wee bit more detail. Why is it called division of amplitude? Well, it's because if a light wave is coming in, right, remember we're ignoring reflection at the top surface of the top glass. Some of that wave reflects from the bottom surface of the top glass slide. So some of that energy, the amplitude of the wave has been divided. So some of the energy is reflected from that surface and some of the energy passes down through the air wedge, reflects from the top surface of the bottom slide, and these two waves interfere with each other. It's called interference by division of amplitude because that amplitude is divided. There, some of it reflects, some of it passes down and reflects from the top surface of the bottom glass. That interference might be constructive or it might be destructive interference. It depends where you are in the air wedge. Let's assume that we are at that bright spot there, a bright line we see, right? Okay. So what that means is ray number 1 and ray number 2 are interfering with each other constructively. We would have to move our microscope a certain delta x. We would have to move a certain distance, delta x, before the next time we see a similar bright fringe on the interference pattern. And because we're seeing exactly the same thing again, it means, that wasn't very straight, it means that that air wedge has increased. The light must have gone down and back up again through a greater distance of equal to one wavelength. So that air wedge has increased by half a wavelength. Down and back up is one wavelength. Now we've two similar triangles here. We've got this triangle, D and L, and we've got this triangle. And with similar triangles, we can do a little bit of mathematics, right? Let's do L over D. If L over D will be the same as, that's horizontal side over the vertical side, will be the same as delta x over lambda over 2. And then if we rearrange it to get delta x on its own, then delta x will be equal to L over D lambda over 2 equals delta x, or delta x equals lambda L over 2D. That relationship is on your relationship sheet. You can use that relationship to work out any of those unknown quantities. D is the thickness of whatever material is making your air wedge. L is the length of the glass slide. Lambda is the wavelength of the light. Delta x is the distance between any two consecutive bright fringes or dark fringes. We don't need to worry about phase change and reflection at any particular point here, as long as we are only looking at fringe separations. So Hopefully that makes a wee bit more sense. It's similar triangles, and from the geometry of those similar triangles we can derive that relationship. You just need to be able to use that. We'll try some questions. See you in the next one.